In this episode, we examine the engineering science of anaerobic digestion, biogas upgrading, biosolids stabilization, and advanced resource recovery. Transforming raw organic solids into renewable energy and high-grade fertilizer requires strict adherence to biochemical fundamentals, precise thermal and hydraulic control, and proactive management of operational instabilities. Whether you are designing a new facility upgrade or troubleshooting an existing digestion train, understanding the interplay between microbiology and reactor hydraulics is essential for turning liability into value. At the core of anaerobic conversion is a complex, multi-step biochemical cascade operating in the complete absence of molecular oxygen. This process is orchestrated by specialized microbial consortia working in syntrophic harmony across 4 distinct stages. The first stage, hydrolysis, is typically the rate-limiting step for complex particulate organic matter. Extracellular enzymes secreted by fermentative bacteria break down insoluble complex carbohydrates, lipids, and proteins into soluble monomers such as sugars, long-chain fatty acids, and amino acids. During the second stage, acidogenesis, facultative and obligate anaerobic bacteria convert these soluble monomers into volatile fatty acids, alcohols, and intermediate organic acids alongside carbon dioxide and trace hydrogen. In the third stage, acidogenesis, acidogenic bacteria transform these acidogenic products into acetic acid, hydrogen, and carbon dioxide. Finally, the fourth stage, methanogenesis, is driven by strict archaea called methanogens, which consume acetate, hydrogen, and carbon dioxide to produce methane gas. Maintaining a delicate kinetic balance between acid producers and methane consumers is the single most critical challenge in digester management. If acidogenesis outpaces methanogenesis, volatile fatty acids accumulate, threatening process failure. When designing or operating an anaerobic digestion system, selecting the appropriate thermal regime governs both biological kinetics and energy balance. The industry standard remains mesophilic digestion, typically operated between 35 and 38 degrees Celsius. Mesophilic systems offer robust process stability, lower heating energy requirements, and resilient microbial populations capable of tolerating minor organic and hydraulic shocks. Solids retention times in mesophilic digesters are generally maintained above 15 to 20 days to ensure adequate growth rates for slow-growing methanogenic archaea.
The primary energetic output of anaerobic digestion is biogas, a gaseous mixture composed primarily of 55 to 70% methane, 30 to 45% carbon dioxide, and trace impurities including water vapor, hydrogen sulfide, and siloxanes. To harness this gas for beneficial use, whether through combined heat and power engines, boilers, or direct injection into natural gas grids, comprehensive biogas conditioning is mandatory. Moisture removal via chilling or desiccant drying prevents acidic condensate formation in downstream piping and combustion chambers. Hydrogen sulfide, generated from sulfate-reducing bacteria in the sewer network and digester, must be removed to prevent sulfuric acid corrosion and sulfur dioxide emissions. This is achieved through iron sponge filters, biological desulfurization, or liquid redox scrubbers. Furthermore, volatile organic silicon compounds, or siloxanes, derived from consumer products and detergents, must be extracted using activated carbon adsorption. Unchecked siloxanes combust into abrasive silica ash that destroys internal combustion engine valves and turbine blades, underscoring the necessity of robust gas scrubbing. Ensuring long-term stability in an anaerobic digester requires continuous monitoring of core process control variables. Operators rely on a suite of physical, chemical, and biological parameters to detect early signs of operational stress long before catastrophic failure occurs. The primary telemetry parameters include digester temperature, hydraulic and organic loading rates, solids retention time, biogas production volume, and methane composition. Chemically, reactor pH must be maintained within a strict neutral window between 6.8 and 7.2. However, pH alone is a lagging indicator. By the time pH drops, severe acidification has already occurred.
Therefore, engineers monitor the volatile fatty acid to alkalinity ratio as a leading stability metric. Total alkalinity, provided primarily by bicarbonate species, buffers the system against acid accumulation. A healthy digester maintains a VFA to alkalinity ratio below 0.3. When this ratio climbs above 0.4, it signals an imbalance between acid-forming and methane-forming bacteria, necessitating immediate operational intervention, such as feed reduction or alkalinity supplementation.
Equally troublesome is biological foaming. Driven by filamentous bacteria such as Microthrix parvicella, excessive surfactant concentrations, or changing lipid fractions in the influent sludge, stable foam blankets form inside the reactor headspace. This foam can engulf gas mixing systems, plug pressure relief valves, and escape into gas collection headers, creating explosion hazards and severe operational disruptions. Mitigation strategies include polymer addition, anti-foaming chemical dosing, operational adjustments to solids retention time, and enhanced primary clarification to remove grease precursors before they enter the digestion train. Beyond energy recovery, the processing of digested sludge into high-quality biosolids is governed by stringent regulatory frameworks designed to protect public health and the environment. Stabilized biosolids must satisfy strict criteria for vector attraction reduction and pathogen destruction. Regulations categorize biosolids into Class B and Class A. Class B biosolids require reduced pathogen levels and vector attraction controls, but impose strict site restriction rules regarding public access and crop harvesting following land application. Class A biosolids, by contrast, undergo advanced thermal or chemical treatment to reduce pathogens to below detectable levels, allowing unrestricted beneficial use in agriculture, landscaping, and retail soil amendments. Achieving Class A certification often incorporates advanced thermal hydrolysis pretreatment, or THP, prior to anaerobic digestion. THP subjects the sludge to high temperatures and pressures, rupturing bacterial cell walls, solubilizing complex organics, and drastically reducing viscosity. This enables higher organic loading rates, enhanced volatile solids destruction, superior dewaterability, and reliable pathogen eradication, successfully bridging the gap between waste management and beneficial reuse.
Rather than letting struvite precipitate uncontrollably, modern facilities harness dedicated crystallization reactors for controlled resource recovery. By dosing magnesium salts and adjusting pH within a fluidized bed reactor, dissolved phosphorus and ammonia are precipitated into high-purity struvite pellets. Struvite serves as an exceptional slow-release, premium agricultural fertilizer, turning a recurring maintenance headache into a sustainable revenue stream and helping close the global phosphorus loop. Implementing advanced anaerobic digestion and resource recovery is never a one-size-fits-all proposition. Project managers and consulting engineers must evaluate a rigorous site-specific decision framework. Capital expenditure for digestion and thermal pretreatment facilities is substantial, requiring thorough techno-economic analysis to balance upfront investment against long-term energy savings, tipping fee revenues from co-digestion of high-strength organic wastes, and reduced biosolids hauling costs. Key decision factors include plant capacity, influent solids characteristics, local energy tariffs, and regional biosolids disposal regulations. Smaller facilities may find conventional mesophilic digestion economically prohibitive unless integrated into regional centralized hubs or paired with food waste co-digestion to boost gas yields. Conversely, large metropolitan water resource recovery facilities can readily justify advanced thermal hydrolysis and gas upgrading infrastructure. Careful risk assessment, pilot testing, and lifecycle cost modeling are indispensable for ensuring that resource recovery projects deliver sustainable financial and environmental returns. The transformation of wastewater treatment plants into active water resource recovery facilities represents one of the greatest engineering achievements of our era. By mastering the biochemistry of anaerobic digestion, optimizing process control parameters, and implementing targeted resource recovery, engineers are turning environmental liabilities into renewable energy, clean water, and vital agricultural nutrients. Thank you for joining us on Water Atlas. In our next episode, we will dive deep into the
cutting edge of industrial wastewater treatment technologies and emerging membrane bioreactor technologies. Until then, keep engineering with precision.